Khan from Khan Academy. What do you think about Khan's style? He's got a nice voice.
All right. So this was your guys' homework assignment last night to go through and start looking at. How many people got values for anything?
I couldn't read what I wrote. I took a picture at one point. I looked at it, and then I went to work.
That's okay. So we got one. We got equations? Okay. So let's start with the equations. So we're going to go with loop A to start with. And we want to write the Kirchhoff voltage loop equation for A. So again, it doesn't matter where we start as long as we start somewhere on the thing or on the loop and into it. Just for kicks and giggles, I'll start up here with this one. So the first thing we run into is R1 times IA. Is there anything else associated with R1? Minus R1 IB. Right, KVLA.
I only remember that because like the first time, 4 times I looked at it, I thought it was Kula, and I'm like, with my.
Okay. So is there anything else we have in R1? Nope. So then we can move on to the next one, which is R5. So it's going to be plus R5IA and minus R5IC minus 15 equals 0. Which one? What about R3? Do we go through it though? Nope. So in this loop, A doesn't even deal with R3. So now, let's put the values to this guy and then we'll condense it down. So we have 100 IA minus 100 IB. R5 is 150, so we have plus 150 IA minus 150 IC equals 15. We combine all of them together, so we have 2 IAs. So we're going to have 250 IA minus 100 IB minus 150 IC equals to 15. There's our first equation. You get that one? Okay. Did you get that one, Jameson? Okay. Anybody else, when you did it, get this equation? Yes, no, didn't do it? Okay. Fair enough. So the next one, we're going to do the Kirchhoff's voltage loop for B. So again, it doesn't matter where we start, as long as we start somewhere on that loop, go all the way around back to our starting point. So the first thing we run into is an R1 IB. Does anybody have any problems if I put the values in as we go? Okay. Then we are going to subtract 100 IA. Then we're going to come around. The next one we run into is R2, which is 1000. So plus 1K IB. And that's the only thing we have going through R2. And then we come back around, we run into R3 plus 150 IB minus 150 IC, all equal to 0. Now we're going to combine all of our terms together. So we only have 1 IA, we've got 3 IBs, and we have 1 IC. So we've got minus 100 IA. We've got 100 IB, a 1000 IB, and a 150 IB. That gives us a total of 1.25K IB, and then minus 150 IC equals 0. Does anybody have any questions about that? Then the last one is the Kirchhoff voltage loop for point C, or for loop C. We can start anywhere we want, follow the path, come back around. So the first thing we have is a 1000 IC, which is R4. The next one we have is an R5. So we have 150 IC minus 150 IA. And then the last resistor we have is R3. So 150 IC minus 150 IB. And that is all equal to 0. Exactly. I know, right? Okay, so now we're going to combine everything together. So we got our ICs, we got our IA, we got another IC, we got an IB. So we end up with a negative 150 IA, a negative 150 IB. Okay, and then we have a 1000, a 150, and a 150 IC. We set that all equal to 0. Why is that? Well, good. Now we can increase your knowledge. Okay. Anybody have any questions or concerns with getting these three equations? Okay. Now the next step is what we need to do is we need to combine these together. Since we have three equations, we're going to do this twice, and we're going to use two sets of equations to condense it down to give out one of the variables. So one of the ways I like to go with this is I'm going to combine 1 and 2 together, and 2 and 3 together. Yep. Yeah, combining all three doesn't work. You want to do it in sets of 2. So if you have 4 equations, you'll do 2 and 2. Then you have 2 new equations. You'll combine those 2 together as you eliminate variables out. So the first thing we're going to want to do is eliminate one of these variables. Do we want to try and eliminate IA, IB, or IC from the first set? IC? Okay. So the first thing we're going to do is combine 1 and 2 together to get rid of IC. Then we're going to combine 2 and 3 together to get rid of IC as well. That way we have 2 equations, 2 unknowns. So the first one we have, do what? Yeah. So we're going to start with 250 IA minus 100 IB minus 150 IC, and that is equal to 15. Our number 2 equation was minus 100 IA plus 1250 IB and minus 150 IC That's equal to 0. So getting rid of IC, what do we need to do? And like what Max was saying is we need to get rid of the ICs, make them equal magnitude, opposite polarities. We multiply this whole thing by -1. That's going to make the 150 IC positive. This is going to change this guy to negative on IB, and we're going to change IA to positive. Then we add them together by going too fast. Okay? We're going to add them together, so we get 350 IA. We get a negative 1350 IB. The ICs will cancel, and that will be equal to 15. Now, we're going to combine 2 and 3 together. So this gives us our fourth equation here. Everybody good here? So we're going to take equation 2, which was 250 IA minus, I get these right. Oh, I did 1 and 3, that's what I did, but that's okay. We can do it either direction. So we have 250 IA minus 100 IB. No, this is 2 and 3. I still wrote the wrong one down. My notes, I flipped them, I did a different set, but it doesn't really matter which set we do. Sorry, negative 100 IA plus 1.25K IB minus 150 IC is equal to 0. And then 3 was negative 150 IA minus 150 IB plus 1300 IC equals 0. Now again, since we already decided this on the previous equation, we want to get rid of the IC value. So the first thing we're going to look for, well, they are already opposite polarity, so that's a help. We already have half of what we're looking for. Now we need to get 150 and 1300 to be equal multiples. Yes? Okay, what was the multiple you had to bring for that? Okay. $3.98. Okay. Come on, give me the thing. So the top one you did by 26 and the bottom one by 3. Does everybody see that? Just got to work out the multiples, find out which one you can get to work. Splitting it up, factoring it, that's one way to get it done. All right, so we'll go through, we'll multiply this out. So we end up with a negative 2600 IA plus 32.5K IB minus 3.9K IC equals 0. Then we carry the 3 through, so we get negative 450 IA minus 450 IB plus 3.9K IC, and that is all equal to 0. Any questions here? Okay. We'll combine these guys together. IC will drop off just like we want it to. We end up with negative 3050 IA then we end up with a 32050 IB equals 0. This gives us equation 5. Yep. So we were able to combine our 3 formulas down into 2 with 2 variables each. Now we're going to combine these guys together to get rid of one of these values. Do we have an easy one? Not really. Going to have some big numbers when we get done with this. So we got 350 IA minus 1350 IB equals 15. And we have negative 3050 IA plus 32050 IB is equal to 0. Which one do we want to get rid of? Get rid of IA. So what do we need to do to each of these to get them to the correct value? Probably brute forcing it. Not evenly anyway. So by 10 wouldn't quite get us because we need to go to 3050, not the 3500. Yeah, it will simplify down. It's just there's larger numbers to worry about. Do what? That's the common multiple? Okay. Nope. Okay. First, the easiest thing to do at this point is we're going to knock off one of the zeros when we multiply them, because we're not going to multiply both sides by the 3050. We're not going to multiply by 350. So we can multiply this side by 35, and we can multiply this side by 305. That'll give us 1. That way we can keep our number somewhat smaller. We're both divisible still by 10, and we have that value. Was there another common multiple in there? Or? Okay. We can go this direction. That's going to require a little more math on my part. So we multiply this side by the 3050, the 305, and we multiply this side by the 35. They can still both have that extra 10 multiplied into it. Since both end of the 0, we can just cut it off and simplify our numbers a little bit. So we take the 350 multiplied by 305. That's going to give us 106,750 IA. We're going to subtract 411,750 IB. And that's going to be equal to 4575. Now there's a reason I'm doing this. I'm breaking these out instead of just putting them into standard engineering notation, is I don't want to lose any of this data. I don't want it to round off. So that's why I'm keeping multiple digits and a lot longer than what we would normally keep. Okay, our bottom. So negative 3050 times 35 gives us a negative 106,750 IA. The 32,050 times 35 is going to give us a larger number. So we got, that's going to be a plus 1,1,2,1,750 IB. So 1 million equals 0. At least we can all multiply by 0 in our heads. Now we're going to combine these guys together. IA is going to drop off. So we end up with this value minus the 411,750. Huh? I wish I did. This ends up being 710K IB. So we come out to at least a nice even number by keeping all of our extra digits. That's going to be equal to 4575. So we've got 4,575 volts divided by 710 kiloohms. So we divide those out, and our IB is equal to 'It is a process, but like I said, when we're done with this, it's going to real quickly give us the answers. And it's a more of a logical approach than Thevenin or any of the other ones we've talked about. Thevenin follows its own set of rules. These you can logic your way through. Because at this point, yes. So the electronics portion, that's the thing too about this. The electronics portion of this problem are these three formulas. After that, it's just algebra. Okay, so we end up with these values. So we have IB is equal to 6.444 milliamps. And one of the good things is IB is positive. So we know that it's going the right direction. So now we're going to take this value and we're going to go back to either our equation 4 or 5, doesn't matter which one, back to these originals, plug in 6.44 here, and solve down. Let's plug it into equation 5. So we're going to do the minus change colors. So the minus 3050 times IA plus the 32050 IB, which is 6.444 milli. That is equal to 0. So we multiply that out. We get minus 3050 IC plus 206.530 equal to 0. We're going to move IC over so we can make it positive. Just do that in all one step instead of having to divide by a negative later on. So IC, is that what we're on? Yes, IA. IA, I thoroughly confused myself too. IA is equal to 206.530. So we just moved the IA across. We divide both sides by the 3050. I added 3050 IA to both sides to get rid of it so we didn't have to divide by a negative number. Either way you're dividing by a negative. This, I like adding instead of dividing by negatives. So 206,530, we divide it by the 3050. IA comes out to be a positive 67.715 milliamps. Okay. Everybody else getting that number? Okay. So now that we have that, we have two of our three values. And so far, everything is positive. I believe you could have. I believe everybody can. Okay? Any questions about this value? Okay? So now the next part, we need to go back and we need to get our original equations and solve for our last remaining variable. Again, we can go back to any of them. I'm going to use our first equation through loop A. So we have 250 IA minus 100 IB minus 150 IC equals 15. So now I'm going to plug these values in for the ones that I have and we'll solve for IC. So we have 250 times IA, which is 67.715 milliamps. We have minus 100 times IB, which is 6.444 milliamps, minus 150 IC is equal to 15. So the 250 times the 67 milliamp one is 16.929 volts minus 6.444 volts minus the 150 IC equals 15 millivolts. $644. Oh, yep, because I added one too many zeros on mine. I typed it in as 64 millivolts instead of the 6.4 millivolts. So we end up with, we'll combine those guys together to give us one value. So the 16,929 minus the 644 millivolts gives us 16.285 volts minus 150 IC equals 15. I'm going to move the IC over and move the 15 over just so it's positive. So the 16.285 volts minus 15 volts is equal to the 150 IC. So we end up with 1.285 volts is equal to 150 times IC. Divide out our 150 ohms. We have volts divided by ohms, so we know we're going to get current. 8.567 milliamps. And is it positive or negative? Positive. Okay, now we'll go through and solve this guy. So we're going to come back to our original circuit. We're going to put in our currents. So we got 67.715 milliamps. We got IC is 8.567 milliamps. And R and B is 6.444 milliamps. So now we have to go through and solve for each of these voltages across these guys. So R1, looking at just current A, what's the voltage that we have across R1 from current A? Yep, so we got the 6.772 volts. Come in this direction. And then what do we have across R5? From loop A, just from loop A. We got 10.157 volts, just from current A. Now we got to look at current B. So R1, we're going to solve for that. So we have 100 ohms times the 6.444 milliamps. That's going to give us 644.4 millivolts. Across the 150, it's going to give us 966.6 millivolts. And across R2, all we have is IB. for R2. So the only current we have going through B is this guy. So that is going to be the voltage for R2. Then we want to look at what our voltages are for loop C. So R3, we've got the 567 milliamps. We're going to multiply that by the 150 ohms. That gives us 1.285 volts. R4 is all it has is RC, or IC. So we're going to have 8.567 volts. Now, looking at that right now, what's the voltage of R2 and R4 if we were to add them together? 15 and change, like 0.001002. So right now, as we're looking through this, we can start to see if our answers are making sense, because we can start to Kirchhoff them. So these two we know only have those individual currents. We come around, we got like 15.001 volts. So our Kirchhoff works out. Then the last one we have is R5 and the voltage induced by current C. So we have 150 ohms, multiply it by the 8.567 milliamps, and we get 1.285 volts. Now, what we need to do is we need to solve for the total voltages across each of these resistors. Now we've solved individual loops, what's going on there. So, R1, we have IA is going down, IB is going up. So what are we going to do with those voltages? They're going to subtract from each other because they're opposing each other. So the net voltage we have across this guy is 6.128 volts. R5, we have 10 volts coming down, and we have 1.28 volts coming up. And again, which one's going to win? This guy will, and then this guy's going to. So our polarities are going to be like this. Same with these guys over here. So we have 10.157 going down. We have countered by the 1.285. That gives us a net here of 8.872 volts. Now again, what do we get when we add R1 and R5 together? We get 15 volts. So now we can make another loop here to double check our answers. We have this voltage, we have this voltage. Together, those add up to exactly 15. The last one we have is across R3. So we've got 9.666 millivolts going this direction. We have 1.285 volts going this direction. So what polarity is R3 going to be from left to right? Positive to negative. Because at the very beginning, when we drew our loops, we assumed a conventional current flow, which was positive first. So we have the 1.285. We're going to subtract out the 0.9666, and we're left with a net of 318.4 millivolts in this polarity. Yep. So if we did one other Kirchhoff loop to check, we're going to have 15 volts total. We have the 6.128, the 0.318, and the 8.567. We end up with 15.0 volts. Now those 13 millivolts is not an issue. We're less than 1% of our total value deviation off. That can just come from rounding. So I wouldn't be too stressed about 15 millivolts in this instance. So we've gone through, everything's checked out. We have Kirchhoffed it to verify that all of our values are correct. And there we have our bridge circuit solved without having to Thevenize, without having to remove anything. We can be able to just solve for it. Two different methods, two different ways to go about it. Some people like this one more, some people like Thevenin more. It just, at that point, it's kind of a personal preference when you want to use these in the workplace. The idea here is we can take a complicated system like this and we can use mesh to solve it. We could put as many loops and as many branches on this thing as we wanted to, and we could still come back and just use mesh to solve for everything. We could go through a loaded or a bipolar loaded voltage divider and solve it using mesh instead of calculating our bleeder and going through the individual nodal analysis. We could. Ouch. Any questions? Okay. If you need to finish up your notes or anything on that, go ahead. Let's go ahead and take a break early. 5-7 minutes, and then once we're done there, if you guys have any questions, we can go through another one of these, or we can move on to the math section and save that for another day. So I'll let you guys think about that while we go to break.